So again, I'm Nick Knight. I'm the technical lead of the software performance team at SiFive, and my talk title is The Direction and Magnitude of SiFive Intelligence. Now, that's a little bit of a joke. I'm talking about vectors. What is RISC-V? Well, SiFive is actually co-founded by the RISC-V architects. RISC-V was a new open ISA, which was developed originally based on a desire to have an open architecture and to be extensible for computer architecture research. Again, the co-founders of the architects of RISC-V went on to co-found SiFive. Now, originally it was designed to be extensible for computer architecture research, but from the very beginning, we had vectors in mind. The joke is that the V in RISC-V, the V is a Roman numeral 5 because it's the 5th iteration of the Berkeley RISC project, but it also is a pun because it kind of also stands for vector. The architects had vectors in mind from the very beginning. That's one of the key features of this ISA. And so it should be no surprise that SiFive is a key contributor to the RISC-V vector ecosystem. I'll be abbreviating RISC-V vector extension by RVV throughout this talk. The vector extension task group chair is Kirsty Asanovich, our chief architect, and we also have substantial in-house support for the RISC-V GNU toolchain. We were the ones who added the RISC-V vector support, and that's now upstream. Right, so in summary, we have RISC-V architects are SiFive employees, and many of them, and we're a key contributor to the software ecosystem. Now, my point of this is that we have a lot of expertise on RISC-V, and we're bringing that to you through our SiFive Intelligence brand, which is also called VI series, which are our vector processors. And that's what I'm here to talk to you about today. So what are RISC-V vectors and why should you want to use them? Well, let's think about packed SIMD. Packed SIMD is an inefficient approach. Really, packed SIMD ISAs will have a big startup overhead, to pick the right code variant, depending on alignment, array size, and array length, and things like that. It also has a large code size to handle bookkeeping. For example, odd-sized application vectors and the prologue and epilogue for software pipeline. So to accelerate the SIMD code, and also to accelerate SIMD ISAs, periodically what design architects do is they double the SIMD register width. The problem about this is for backwards compatibility, so does the instruction set. For example, IA32 grew from about 80 to about 1,400 instructions since 1978. That was largely fueled by this exponential growth in SIMD instructions. Do you remember what VFMAD 213 PD means and when's the right time to use it? There's a huge amount of SIMD instructions. It's a huge cognitive load on the programmer. So in comes RVV to the rescue. The two key features I want to emphasize in my talk today are the dynamically reconfigurable vector register file. I'll be giving you some examples of this. The idea is you can change the vector length and the data type at runtime. And moreover, you can actually group registers, the architectural vector registers, together into longer logical registers by a length multiplier that I'll call LMUL. And the other key feature I really want to emphasize today in this talk is that when you write RISC-V vector code, you have portable code. It works for any vector length. So let's see this by an example. First of all, let me just give you a little background here. We have 32 vector registers in the RISC-V vector extension, and each of the vector registers is, I don't know if you can see my mouse cursor, so we'll use words. Each vector register is VLEN bits long. VLEN is the vector length, and it's in bits. That's an implementation defined parameter. The implementer, the designer, gets to pick that based on their own understanding of the application space and hardware trade-offs, et cetera. What's interesting here, though, is you'll notice is that in addition to the vector registers, we have two control registers down here, a vector length register and a vector type register. Again, we offer dynamic vector length and dynamic vector type. You can change them at runtime. Let's see how this works. So let's look at an example here. Memcopy. We'll do vector memcopy. We have a destination in the first argument, A0, the first argument register, that's the destination vector. The source vector that's getting copied into the destination array is in A1, and A2 is the length. So on the top is the C prototype you might see. Moving down into the code, you'll see that the first thing we do, of course, is back up the destination pointer to the output, and then we drop into the main loop. Right off the bat, we call a vset VLI instruction. What this does is this sets the configuration, and this also calculates the strip mine length. So we're asking the processor for 8-bit vectors, vectors of 8-bit elements, so single byte elements. And we're actually passing in A2 here. That's the whole length of the array we want to copy. Internally, the vector processing unit is going to strip mine this loop by picking whatever the maximum length it can up to VLEN, or up to whatever's smaller, VLEN or N here. And it returns in T0, the temporary register T0, what it actually ended up picking. Now we'll drop into the code. We just do the load, vector load, some bumping pointers around, and the vector store. That's the meat of the mem copy. And then we do a little bit more, bump the second pointer and loop back. What you'll notice here in this example is that there's no VLEN anywhere in the code. The programmer did not have to mention the vector length anywhere. The same binary machine code can run on any RISC-V vector machine. It handles VLEN implicitly. So that's really, if you, like me, you spend a lot of time optimizing loop nests, that's huge. There's no boilerplate at the beginning to figure out how to chunk this up into SIMD length things. And it really saves a lot of effort on the programmer, and it's also helps binary compatibility. You don't need to recompile your code. It'll run fine on any other machine. So like I mentioned, there's more. There's a vector length multiplier. Vector register groups can operate as single vectors. And this is very useful for accommodating NICs with operations like widening operations, where you need a longer vector, where your output has more data, more bits than your input vectors. But another key, perhaps the more important key here is that you can leverage longer vectors to increase efficiency. Of course, there's a trade-off because you'll increase register pressure. There's always trade-offs. But this is a really huge technique. So in this example here at the bottom, this is doubling. There's two 16-byte registers with a 4-byte data type stored in them, and they're being reconfigured as a single 32-byte register. Now, how does this work on our memcopy code? It only changes, well, these 3 characters here, the comma M8. Everything else stays the same. All you have to do to take advantage of this length multiplier is just change the set VL instruction at the top here. That doesn't change anything else in the code. So it's very easy to take advantage of this new feature. Again, this is portable code, can run on machines with any vector length. That's a really huge feature of RISC-V vectors that I want you to get out of this talk, this portability and ease of programming. Of course, there's a bunch of other useful features. I lead the software performance team, so we demand having a rich set of linear algebra primitives, scalar, vector, vector, fuse, multiply, adds, reductions, operations of that type. But some other interesting features about this vector ISA is that operands can be sourced from the scalar register file. You don't have to worry about splatting things. And another really cool feature we have is the segmented memory operations, which are for loading structures, arrays of structures like complex number pairs and RGB values. Can handle up to 8 field structures. They might be non-contiguous because we've got strided and indexed variants of these that can pull structures from non-contiguous layouts. And I guess the other point I want to emphasize here is that this is not an accelerator I'm talking about. This is a single instruction stream with program order memory access. You're not writing a kernel to be dispatched on some other piece of hardware. And so this means you have a single development environment. It's really easy to program. Now, our roadmap for the next 18 months, we have a couple different VI series offerings. We're going to have an IoT offering called VI2, an edge offering called VI7, and a data center targeted offering called VI8. These are kind of spanning the design space from microcontrollers to application processors. As I've just discussed, these are configurable in software by the RISC-V vector extension, but they're also configurable in hardware, depending on what your needs are. Talking about the VI2, for example, I'll focus on that here in the interest of time. This has support for element data types. It's targeting DSP and general compute applications, but looking at integer, fixed, and floating point computations with 8 to 32-bit width. And our microarchitecture is leveraging the scalability of the ISA. The initial config has 128-bit data path, 512-bit VLEN, but again, remembering LMUL, that increases effectively by a factor of 8, up to 4K bit vectors. And also, as I mentioned, the data path width and the VLEN data types, these are all configurable parameters from SiFive. I should mention that SiFive, we can leverage our existing core IP debug and trace hardware solutions. So you can easily work with third-party tools, and our Freedom Studio software will format and display the vector and control registers for you too. Now, 128-bit data path, and for 32-bit floats, that means you could do 4 floats per cycle, right? So you expect a vector speed up to give you 4x. No, it's actually a lot higher because remember we have the memory port is wider, and we have this pair. We have a separate vector and scalar pipelines, separate compute and memory pipelines. So you can actually get a lot larger speed up than what you might think naively on, for example, some floating point DSP kernels here. This is from a very later simulation using that VI2 configuration I just discussed. This is a speed up of our assembly routines over C sources, which were compiled to a scalar target. And you see a wide range of different speed ups here, but they're definitely getting good speed ups, more than you might expect by just raw floating point speed up. Again, that's because parallelism in the microarchitecture. Matrix multiplication, it's really easy to hit peak efficiency on this thing. This is compared to F floating point peak, which is just the FPU being lit up the whole time, n cubed over 4 cycles, because n cubed operations and 4 floating point operations per cycle. You can see that we're getting almost 100% of peak at about 512 problems. This is again on the VI2 SGEM. I'd like to take the last 5-6 minutes to talk about intelligent vector software. We have 3 programming styles here. We're anticipating at SiFive. The majority of our programmers are going to use auto-vectorization and tuned libraries. And a minority we expect to use manual vectorization with Intrinsics, and a special few will be using handwritten assembly. But whatever category your style falls into, you have the same advantage of RVV, the performance portability across hardware platforms. And you don't have to recompile your code. Your binaries will perform better on faster hardware, and they'll continue to work on smaller hardware. Now, the point of this slide is mainly that there is an extensive literature on vectorizing compilers. Peak performance and actual performance often differs dramatically, but with the right compilers, getting a large percentage of peak is possible on vector processors. Now, this is some old data I have on this slide here from 1989, might be before some of you guys were around, but it's still relevant today. And it's showing you that the compiled code can get, just naively compiled code can get close to half a peak, and you can do a lot better with a little bit more intelligent compilation. Now, vectors and vector technology seem to have been largely forgotten in the 90s and early 2000s, but the technology from 70s and 80s is still there. It's still valid. So we have a lot of, we can really stand on shoulders of giants here with auto-vectorization. Say this in a different way, we envision most of our users are going to write scalar C and C++ code and rely on the compiler. Now, auto-vectorization is well understood, and the RISC-V vector extension is really amenable to all the standard loop nest optimizations. Moreover, the flexibility really simplifies the code generation. As I mentioned, we're the leading developer of the RISC-V GCC port, so we have a lot of in-house expertise here. And simultaneously, my team is developing our performance libraries like BLAS and FFT, things like that. Now, like I mentioned, some programmers are going to want more fine-grained control over the compiler vectorization. And our Intrinsic solution exposes the RISC-V vector assembly to the C and C++ programmer, but they don't have to write assembly. So users can actually manually vectorize code regions as they see fit, while simultaneously leveraging the compiler for memory management, register allocation, instruction scheduling, things like that. And this is all still compatible with the vectorizing compiler's typical loop nest optimization. For example, let's see how this would work. Here's over here on the left is some C code using our Intrinsics. You can see that we have a for loop. This is a component-wise add of 2 vectors. We set the vector length, load, add, store. And then the compiler generates the assembly using the vector instructions here. So you can work in C and then get the power of the RISC-V vectors. The compiler should be able to do this for you, but here's an example where you might want to take control yourself. This is using LML = 2. You might notice you could crank it up higher in this example. And of course, those seeking the last 10 to 30% are going to use RISC-V assembly. My point here is just that it's a very clean, easy to use assembly language, especially for those of us who've spent time on SIMD. The flexible vector length manages fringe cases, so it's much less bookkeeping code, and it's portable. And again, it's not an accelerator. This is a single instruction stream. What we have prepared is a vector evaluation platform we're calling the VEP. This is a complete evaluation and development environment for our VI series core IP. This is an algorithmic evaluation and porting platform for our customers and partners. This is a package including tool chain, which is our GNU tool chain with vector support, including Intrinsics, some optimized libraries, including our DSP library, which is compatible with CMSIS DSP API, and some highly tuned kernels for fast Fourier transforms and matrix computations, as well as a couple execution models, including a Gem5 performance model and Spike ISA simulator. And over here again, I'm showing you the Intrinsics example from the previous slide. So our customers and partners, please contact us, and we'd love to tell you more about the vector evaluation platform. So the key takeaways of my talk: 2020 is the year of RISC-V vectors, and we have big plans to make that a reality. Our vector VI series processors really cover a wide range of design points and use cases. I think a lot of applications can really benefit from these processors. And SiFive, why go with SiFive? Well, we invest in both hardware and software to enable the solutions. We're leaders in both. And our vector evaluation platform, VEP, is a way to get your hands on the evaluation and development of RISC-V vector, of our hardware and software. So my conclusion: vectors done right now. Now I want to thank the organizers, Bethany Lira, B. Lugo, Mike Demler, and Linley Gwenap for graciously welcoming to this conference, and for their hard work hosting this and switching everything over to the Zoom platform. I appreciate it. And I want to thank all of you in the audience for your attention.
So one of the questions, Nick, was about the compiler support for the vector extensions. I think you've mentioned GCC, but I just want to know if that's available now, or do you have other plans for supporting other software?
So it's upstream in the tool chain. Vectorization work is still under development, but the tool chain, all the RISC-V vector assembly code and code generated from the Intrinsics works just fine.
Okay, so I think went past pretty quickly. You had a slide with the roadmap. What's the schedule for releasing the cores?
Just hide this window to rate myself. The schedule, so I'm not really able to give detailed deadlines. This is over the 18-month time frame is what I'm allowed to say. That you'll see announcements for these. This is not meant to be a formal product launch in this presentation. I'm giving you a heads up on what's coming. So you should expect to see formal announcements on VI2, VI7, VI8 over the next 18-month time frame.
Okay, but some at least for the end of the year.
Yep.
Okay. At this point, do you have any performance benchmarks that you've run?
Yeah, so I showed results for a matrix multiply benchmark, as well as for some DSP routines.
Okay. Maybe this goes along with your 18-month release schedule, but one of the issues will be having a complete software stack. You talk about the libraries being available. They'll be available at launch time before you release the cores. How is that going to go?
Which libraries are you specifically referring to?
I mean, if you're going to compete with any of the other DSP-enabled cores out there, they have specialized packages for various types of functions. You mentioned FFTs as one example.
Oh, so for DSP stuff, for example, we have the DSP library. That's part of our vector evaluation platform. You can put your hands on it if you'd like. It's a vectorized assembly code.
Okay. So the question would be, would software developers be able to get started early?
Yeah, so that's the point. I apologize for rushing through that slide. The vector evaluation platform is intended to help our customers and partners get up and running quickly with RISC-V vectors.
Okay. Yeah, so a similar related question. Somebody from the audience wants to know if auto vectorization compiler is already available. Do you have a date for that?
I do not have a date for that. I think I could provide one under NDA, but I don't have one I can release publicly.
Okay, great. Okay, another question then is to support wider, deeper registers, and this is a long question, so bear with me.
I love it. Yeah, let's go for it.
And your microphone breaks up a little bit when you lean back, so maybe you want to lean in, not to borrow a phrase from somebody from Facebook, but anyways. To support wider, deeper registers and gaps between elements, does the vector processor sacrifice clock rate or read after write bypass hardware complexity. Hardware complexity may result in elements being used in a different position of the dependent source vector element. I'm not sure if that makes sense, or I need to reread that.
No, that's a great question. I'm not going to be able to answer the specific microarchitectural details and the trade-offs that our designers go through. That's a good question, has an answer. I would be happy to follow up over email and have the right people respond to that one. It's a good question, though.
Is it possible for customers to compile their own AI software automatically to SiFive hardware?
That's our goal.
That's it, yes. Can the programmer copy multiple arrays in parallel? If so, how many multiple threads?
Well, threads is a multi-core. Yes, that's a orthogonal question. Copying multiple arrays in parallel is using like the segmented these segmented memory operations. So you can have a array of structures and have load them all at the same time that way. If you have a struct of arrays, then you would have to fire off separate loads to make that work. But this is an advantage. But oftentimes if you're accessing the arrays in a lockstep pattern, the right thing to do is to exploit the spatial locality. Like think of RGB values or complex numbers in a fast Fourier transform. You typically need the corresponding elements of each vector at the same time. You don't want to go walk in the page table to find the imaginary component of your complex pair. So having them in the structive arrays format is actually beneficial for spatial locality, and this is leveraged fully with our segmented memory operations. I think that's the right way to structure your program.
Okay. Question again on the software side. You mentioned GCC. Any plans to support LLVM? Yeah, so there is a very active
development in LLVM as well, and we have a number of patches upstream there already. We have an LLVM team.
Okay, so I was also curious. I don't know, since you're on the software side, the question would be, how would you compare the competitive targets you're going after? It would be a comparable Cortex-M class CPU. What do you think?
Well, we have for our vector units, and what I'm talking about here today, we have a wide range of different targets. The VI series has, the large design space from IoT stuff to full application processors. So I think we're really trying to cover the design space. I guess all of the above is the answer.
Sure. Question on the runtime variability of the vector length, subject to the physical vector registers. How do you architect your design to support that?
I'm not entirely sure I understand the question. So let me just say that we have the vector length and vector type registers are in the ISA, and that's where that information lives.
Right. But does the programmer need to know the physical capacity of the vector stack? The vector register.
The software does not need to know any microarchitectural details about the register file. That's the whole point, is that you just write code that works on any RVV platform.
Okay.
I'm not sure I fully understood the question.
Well, I mean, there's a physical limit in the number of vector registers you have available.
Oh, no, so yes, okay, yes, there's 32, the base vector ISA is 32 vector registers. A future 64-bit extension of the vector extension will increase that number of registers. There's 32 registers, but they're configurable in length, and because you can double, triple, quadruple, et cetera, them with LMOL, you can have much, much longer vector registers.
Okay,
so.
Okay. Yes, somebody's asking about similarity between vector extensions in RISC-V and ARM. You mentioned SimSys support. From the programmer's point of view, you're trying to make it as transparent as possible, I suppose.
Yeah, what was the question?
About similarity between RISC-V vector extensions and ARMs. And ARMs got their new Helium extensions.
They've put in a lot of work on their SVE and its extensions too. What I'm not really prepared to talk about ARM's offerings. I'm here to talk about SiFive's offerings. What I'll say is that they're not making RISC-V chips, and we are.
Okay. Right. Is there a recovery mechanism for floating point errors during computation?
Yes, we have a full IEEE implementation.
Got it. Okay, another question about if you fire off multiple vector loads, do they serialize at the read data memory interface or at the vector register file write interface? That's a detailed question again. We have a DSP expert in the audience, I'm sure.
Yeah, those are really good questions. And I'm, I'm thinking because about how they might differ across our different microarchitectures. But I should take a step back and say I would need to follow up on these with our with the right people. It's a good question, but I'm not prepared to answer it right here on the spot.
So the question, I think this is similar to what I was exploring with you a minute ago. What if the program requires a vector length that's longer than the CPU configuration? How do you handle that?
The program, I mean, that was the memcopy example. The user could pass in any length array, and it's gonna the hardware is gonna strip mine. That's the whole point. Is that the hard? I mean, it's a good question. Let me reemphasize the point. The for loop, the for loop is being strip mined in hardware. The hardware decides what vector length to use, handles the fringe case at the very end, or maybe the last two if it wants. It does the right thing, and the programmer doesn't have to worry about it. So you can have an infinitely long application vector, and the processor will happily chunk it up for you.
Okay, and question more on the hardware implementation side. Can the VI cores support multiple load store units?
I don't know the details of where that falls into our design space. I'd have to get back to you on that one. That's a good question.
Sure. Right. Not really a software question.
That's a very good question. You guys are asking great questions. I really appreciate it.
Yeah, some very technical.
We got some pros in the audience. I could tell.
Yeah. They'll be catching up with you in the break room.
The breakout session. Yeah, look forward to it.
Yeah, I think we have time for one more. It said that a lot of companies are supporting the bfloat format. Are you going to consider that as well?
So we just, we are considering it. We are absolutely thinking about it. I think our first target will probably be, at least from the RISC-V perspective, we have half precision floating point in the spec, and it's supported in our microarchitecture. And I think bfloat's kind of an orthogonal decision. We can certainly make bfloat chips.
Great. Okay, thank you, Nick. I think we'll wrap it up now, and we'll see you later on in the breakout room starting at 12:10.
All right, thanks, Mike.